We have recently obtained new photographs of 3I Atlas, the third interstellar object ever spotted from Earth, currently speeding through our solar system. Now, astronomers have documented that moment live, broadcasting in real-time worldwide, showing them observing all of this. Check this out. Wow, impressive. Yes. Look at that incredible object. 3I Atlas is not acting like any typical space body. It is defying fundamental physics and approaching Earth. Leading observatories globally have paused other investigations to concentrate entirely on this enigma. Is this merely an extraordinary coincidence? Or is there something or someone intentionally attempting to capture our attention? The mathematics of impossibility. At this very moment, drifting through space approximately 400 million miles from Earth, lies an object breaking every rule we believed we understood about the cosmos. 3I Atlas is not just strange. It is mathematically improbable to the extent that some of the planet's brightest intellects quietly doubt whether natural phenomena alone can explain what they observe. When scientists estimate the probability of all the events surrounding this object happening by chance, the figures are so minuscule they become essentially meaningless. This mathematical scenario is akin to a complete stranger approaching a person on a bustling street, calling them by their name, knowing their birthday, and handing over exactly the amount needed to pay a bill due tomorrow. Each individual detail might be unlikely to occur randomly, but when combined, these tiny chances multiply to a number so close to zero that most would assume the meeting was orchestrated. This is precisely the statistical dilemma astronomers confront with 3I Atlas. The object was initially discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS, based in Hawaii. However, what makes this finding exceptional is not just the detection itself. NASA's test mission had actually captured images of the same object months prior, when it was still in the distant outer solar system. Nobody realized what it was until much later. It's like a security camera inadvertently recording a bank heist, only to find the footage after the thieves have publicly announced their presence by entering the police headquarters. The detection software used by both Atlas and TESS processes roughly 40,000 images every night, searching for objects that move relative to the distant stars in the background. These systems depend on advanced pattern recognition algorithms that compare successive photos taken minutes apart, identifying anything that shifts position between frames. The software automatically calculates initial orbits for discovered objects and flags those whose paths don't match known asteroids or comets in the solar system database. This delay in recognition reveals something intriguing about how we hunt for interstellar visitors. Current detection techniques are tailored to find objects that behave predictably, following patterns derived from studying bodies formed within our solar system. 3I Atlas was concealed in plain view because it does not follow these patterns. It was active and luminous when it should have been dormant, shining with unusual colors, and moving along a trajectory that seemed too convenient to be natural. The mathematical scrutiny becomes even more bizarre when considering the timing. 3I Atlas arrives at a point in human history when we finally possess the technology to investigate interstellar visitors in depth. Had it appeared 50 years earlier, we would have missed most of its peculiar traits. If it arrives 50 years from now, we may have superior tools but different priorities. Instead, it has come exactly when we are prepared to detect that something remarkable is happening, yet not quite advanced enough to immediately grasp its significance. The chemistry of extraterrestrial worlds. When researchers examine the spectral signatures of 3I Atlas, they are essentially reading the autobiography of another star system. Every element present in its glowing cloud narrates a tale about the conditions existing when this object first came into being, potentially billions of years ago, in a region of space we might never visit. What this autobiography reveals is a cosmic environment so distinct from our own that it challenges our fundamental assumptions about how planets, and their residual building materials, evolve. The 16:1 proportion of carbon dioxide to water is not merely unusual. It is a hallmark of formation conditions that do not exist anywhere in today's solar system. This implies that 3I Atlas originated in a region dominated by carbon compounds rather than the oxygen-rich setting that formed Earth and its neighboring planets. Such conditions could be found around younger stars that have yet to produce the heavy elements familiar to us, or around older stars that have undergone different evolutionary phases than our Sun. The spectroscopic techniques applied to identify these chemical markers involve dispersing the light from 3I Atlas into thousands of separate wavelengths using high-resolution gratings and prisms. Each chemical element and molecule absorbs or emits light at precise frequencies, creating distinct patterns in the spectrum that act like fingerprints. The most sophisticated spectrographs can detect concentration differences as slight as 1 part per million, enabling astronomers to identify trace elements comprising less than 0.000% of the total composition. The real puzzle emerges when examining the metals. The discovery of nickel without any detectable iron contradicts established knowledge about stellar nucleosynthesis, the process by which elements form inside stars. Nickel and iron are generated together in the same nuclear reactions and dispersed together when stars die. They are so intrinsically linked that finding one without the other is like seeing a shadow without anything to cast it. This separation could theoretically result from natural processes, but would require extremely rare and precise conditions. Perhaps 3I Atlas formed from material already altered by some unknown natural sorting mechanism. Or maybe it originated from a type of star or stellar event we have yet to encounter. The alternative explanation, that this separation was caused by artificial means, opens possibilities that many scientists are hesitant to discuss openly. Optical properties add another dimension of mystery. When light interacts with the dust surrounding 3I Atlas, it produces polarization patterns unlike any known natural materials. This is not simply about the dust differing slightly from what we've seen before. The polarization signature suggests the dust grains possess structural characteristics that would be extraordinarily difficult to form through ordinary cosmic processes. It's as if each microscopic particle has been engineered to interact with light in a particular manner. Why conventional physics keeps failing. Every attempt to explain 3I Atlas using standard cometary physics encounters the same issue. The models work temporarily, accounting for some observed behavior, but eventually hit a wall, where predictions diverge sharply from actual observations. It's like using chess rules to interpret a poker game. Some elements appear familiar, but the overall pattern doesn't fit within the accepted framework. Normal comets obey what astronomers call the inverse square law concerning solar heating. As they approach the sun, the energy they receive increases predictably, causing proportional sublimation of ice and resulting in expected brightness and activity levels. However, 3I Atlas violated this law when detected far beyond Jupiter, exhibiting activity levels that normally wouldn't occur until much closer to the sun. This early activation implies that something inside 3I Atlas responds more strongly to solar radiation than typical cometary materials, or that it contains internal heat sources independent of solar energy. Both scenarios demand explanations beyond conventional comet science. Perhaps it contains substances with much lower sublimation temperatures than usual cosmic ices. Or maybe it harbors radioactive materials that supply internal heat. Either possibility suggests formation conditions vastly different from those in our solar system. The brightness curve poses another problem. Most comets gradually become brighter as they near the sun, following smooth mathematical patterns that astronomers can forecast months ahead. 3 Atlas, however, is intensifying more rapidly and unpredictably than those patterns indicate, with sudden bursts of activity that appear to happen without clear causes. It's like having a dimmer switch that functions normally across most of its range but abruptly jumps to full brightness at random moments. These departures from typical physics become even more noteworthy when you realize that 3-2 Atlas isn't merely somewhat odd. It is peculiar in several independent respects, all pointing toward the same conclusion. The chemistry is off, the physics is off, the trajectory is off, and the timing is off. Any single irregularity might be explained away, but the combination forms a pattern that challenges our current understanding of how natural objects behave in space. The orbital dynamics of intent. Among all the enigmas related to 3 Atlas, perhaps none is more compelling than its path through our solar system. When objects arrive from outside the solar system, they usually follow hyperbolic orbits that take them through our planetary neighborhood at high speed and awkward angles. These random paths reflect the chaotic behavior of stellar motion and gravitational forces within the galaxy. But 3 Atlas is different in ways that unsettle orbital mechanics experts. Its alignment with the ecliptic plane represents a statistical anomaly so profound that some scientists have stopped calling it a coincidence. Calculating the likelihood of an interstellar object arriving on such a precisely aligned course yields odds of about 1 in several million. These odds are not impossible but are low enough to suggest either extraordinary fortune or something more purposeful. Predicting these encounters requires solving complex differential equations that consider the gravitational influences of all major solar system bodies. Modern orbital calculation software uses numerical integration methods that can model the movement of 3I Atlas with accuracy down to a few kilometers over multiple years. These computations demand supercomputer resources and advanced algorithms capable of handling subtle gravitational perturbations from planets, moons, and even large asteroids affecting the object's trajectory. What makes this path even more fascinating is how efficiently it passes through different zones of the solar system. The route carries 3I Atlas past Mars at an optimal distance for observation, then swings it around the Sun at perihelion before arranging future flybys with Venus and Jupiter. Each approach occurs at distances designed to maximize scientific gain while minimizing risks of gravitational disturbance or destruction from solar heating. This efficiency is striking because most natural solar system trajectories are either too close, risking destruction, or too distant, limiting observational chances. 3I Atlas threads the needle perfectly, maintaining distances that allow detailed examination while preserving the object's integrity. It's akin to a cosmic dance where every move seems choreographed for peak scientific value. The timing of these events adds yet another layer to the mystery. 3I Atlas is arriving during a time when humanity has unparalleled tools for studying interstellar visitors, yet it is approaching at a speed that allows sufficient time for preparation and coordinated observations. If it were moving much faster, there wouldn't be enough time to organize the worldwide response underway. If it were slower, it might not create the same urgency driving the current scientific mobilization. The world's top telescopes all look upward. Something extraordinary occurs when humanity's most costly scientific instruments suddenly shift their priorities. The Hubble Space Telescope, which books observation time years in advance, abruptly canceled scheduled projects to focus on 3I Atlas. The James Webb Space Telescope, so highly demanded that astronomers fiercely compete for even a few hours, cleared its agenda as billions of dollars worth of space hardware dropped everything to concentrate on a single target. The situation has clearly gone beyond routine research. This isn't like flipping through TV channels. Each telescope operates on incredibly strict schedules, with every observation minute assigned months or even years beforehand. Changing plans means disappointing other scientists who have been awaiting their opportunity to study distant galaxies, exoplanets, or star-forming regions. The fact that administrators proceeded with these changes demonstrates how significant they believe 3I Atlas could be. But it's not just space telescopes participating in this cosmic vigil. Ground-based observatories, which usually spend their nights photographing various parts of the sky, have formed an impromptu global network, passing 3I Atlas from one telescope to another as Earth rotates. It's like a relay race where the baton is this mysterious glowing visitor, and nobody wants to drop it. The SOHO spacecraft, normally focused on monitoring the Sun, has been enlisted as a special watcher. SOHO wasn't built to track comets, but its unique vantage point provides a front-row seat to observe how 3I Atlas behaves as it nears our star. Engineers had to develop new software just to make this possible, a task they don't undertake lightly. Even more impressive is what's happening at Mars. 2 European spacecraft orbiting the Red Planet are preparing to attempt something for which they were never originally designed. Mars Express and the ExoMars Trace Gas Orbiter plan to photograph 3I Atlas during its October flyby. These probes were built to study Martian weather and geology, not to track fast-moving interstellar visitors. It's like asking a security camera to suddenly become a sports photographer. The coordination required for all of this is staggering. Telescopes in Hawaii hand off observations to others in Chile as Earth turns. Space agencies share data in real time. Astronomers who usually compete for discoveries are collaborating as if they're all on the same team. This degree of cooperation happens only when everyone agrees they're witnessing something that could transform everything. Racing against the clock in October, this isn't just another month for astronomers. October 2025 has become the most critical deadline in modern space science. Every aspect of the 3I Atlas investigation builds toward those crucial weeks when the object makes its closest approach to the Sun. Afterward, the opportunity may vanish, perhaps forever. The Mars encounter will occur first, and it will be unlike anything attempted before. When 3I Atlas passes 28 million kilometers from Mars, it will still be moving at tremendous speed. The orbiting spacecraft will likely have only a few hours to capture images before the object disappears again. It's like trying to photograph a speeding motorcycle from another moving vehicle while both are racing through thick fog. The ultimate test arrives at perihelion on October 29th. This is when 3I Atlas faces the full intensity of solar fire. The Sun's powerful radiation will either expose hidden structures beneath the object's icy surface or possibly destroy what scientists are trying to study. Most comets put on spectacular light displays during perihelion but sometimes break apart entirely. There's no way to predict which fate awaits 3I Atlas. What makes this even more nerve-wracking is that 3 Atlas will disappear behind the Sun for several weeks after perihelion. During that time, no one on Earth will be able to observe what's happening. The object might fragment into dozens of pieces, undergo dramatic changes, or simply vanish altogether, and we won't know until it reappears in December. It's like performing surgery and then having to wait weeks to see if the patient survived. The technical challenges during this period push every instrument to its limits. As 3I Atlas gets closer to the Sun, observation from Earth becomes more difficult due to intense glare. Astronomers are developing new techniques to detect the object at dawn and dusk, when it might briefly be visible despite competing with sunlight. It's like trying to see a candle's flame while looking directly at a searchlight. Please share your thoughts in the comments below. Don't forget to like and subscribe to stay updated on all things 3I Atlas. As December approaches and 3I Atlas reemerges from behind the Sun, the global scientific community will be watching intently. This moment will be critical for determining whether the object has survived its solar encounter intact or if it has broken apart into smaller fragments. The observations gathered during this period will offer invaluable insights into the nature and composition of interstellar visitors, knowledge that could reshape our understanding of the cosmos. Scientists are already preparing contingency plans to adjust their observation strategies depending on what they detect. If 3I Atlas remains whole, telescopes will focus on detailed spectroscopic analysis to study its chemical makeup. If it has fragmented, researchers will track the individual pieces, aiming to understand the breakup process and how these fragments interact with solar radiation and the solar wind. This mission has also sparked discussions about the potential for future interstellar object encounters. With advances in technology and growing global collaboration, the astronomical community is better equipped than ever to respond rapidly to new visitors. The lessons learned from tracking and studying 3I Atlas will help refine detection methods, improve observation coordination, and potentially prepare humanity for more ambitious exploration missions beyond our solar system. Beyond the science, the excitement surrounding 3I Atlas has captivated the public imagination. Social media platforms, news outlets, and science forums are buzzing with speculation, questions, and theories. This rare event serves as a reminder of humanity's place in the vast universe, sparking curiosity and inspiring a new generation of space enthusiasts and aspiring astronomers. Educators are leveraging this opportunity to engage students with real-time science, turning the unfolding event into a dynamic classroom experience. From elementary schools to universities, teachers are using 3I Atlas to illustrate concepts in physics, astronomy, and mathematics, demonstrating how science works in practice and how the universe continues to surprise us. Meanwhile, policymakers and space agencies are taking note of the increased public interest and scientific potential. Funding for space research and planetary defense initiatives has gained momentum, highlighting the importance of investing in our ability to detect and study cosmic phenomena. 3I Atlas has become a catalyst for dialogue on how best to prepare for future celestial visitors, whether natural or artificial. In the background, engineers and mission planners are exploring the feasibility of sending spacecraft to rendezvous with similar interstellar objects in the future. Although challenging, such missions could yield unprecedented data, revealing secrets about the formation of planetary systems and the origins of organic molecules necessary for life. The scientific community is energized by the possibilities that 3I Atlas has unveiled. For now, all eyes remain fixed on the skies, awaiting the next chapter in this extraordinary story. As the comet continues its journey through our solar system, it carries not just scientific value but also a profound message about exploration, discovery, and the boundless mysteries that lie beyond our world.